Hello and welcome to another video. Today we're going to talk about thermochemistry. Since this is the start of our unit on thermochemistry, this video is going to talk a lot about some of the basic material that you need to understand the larger picture of thermochemistry and the more involved topics that we're going to get into later. So today we're going to really kind of get into a lot of the basic terminology and units that are going to be used throughout the course of the unit. One of the biggest things you have to understand with thermochemistry is it's all about energy. So if you recall, we talked about how matter is never created or destroyed. Well, the same thing is true about energy, and this is actually the first law of thermodynamics, which we're going to talk a whole lot more about later in another video. But the main idea here is just that you can't create energy. It's got to be converted from one form into another. And the reason why this is important for chemistry is because all chemical reactions involve changes in energy in some form or another, so we need to make sure we have a pretty decent understanding of it. So what exactly is thermodynamics? Well, thermodynamics is basically the study of how energy changes from one form to the next. Now, in chemistry, for our particular unit here, we're going to be focusing mainly on heat. Heat is a form of energy, and we're going to look at how it transfers from one thing to the next. Now, you might be asking yourself, why is this important? Is this just another thing that Mr. Black is teaching me that I have to kind of pay attention to and get for this test? Well, thermodynamics actually plays a huge role in pretty much everything that you do. When you eat things, that's lots of chemical reactions happening. There's a lot of heat transfer that occurs. When you just move around, you're talking about lots of energy and heat transfer. If you want to drive a car, you're talking about fuel being burned. That's energy transfer. So all the stuff that you deal with on a day-to-day basis is energy transfers, and that's where thermodynamics comes into play. So thermochemistry is just a portion of the broader scope of thermodynamics. We're really going to be focusing in on the chemistry aspect, which is how heat is transferred during chemical reactions, which happens both forming and breaking down of chemicals. So a lot of terms you're going to be using throughout the course of this unit are force, energy, work, heat, and temperature. And they're very important ones. We're going to go through each one individually. Let's start off with force. Force is a push or pull on an object. And this could be as simple as pushing on a box, pulling on a rope in tug of war, or it could be more bigger, like if you look up above, the sumo wrestlers there. Perfect examples of lots of force being pushed around. Maybe they're not so little, and you got that little guy being held up there, but hey, you gotta start someplace. Now in chemistry, if you want to talk about a chemical example, ionic compounds are a great example because you have something called the electrostatic force that occurs. That's the positive and negative relationship between positive and negative ions. It's what holds ionic compounds together. The next big term you have to understand is energy itself. And energy, by definition, is simply the capacity to do work, or in our case, transfer heat. Now, energy can come in lots of different forms, but again, the one we're going to focus the most on is heat. Now, I mentioned work a second ago in the sense that it's basically what energy is, right? Energy is the ability to do work. Well, work is just when you cause an object to move against a force. So you apply a force and that object moves, you get work being done. If you don't move, there's no work. So I could push against a wall forever, and even though I'm like ridiculously strong, if that wall never moves, I'm not actually doing any work. Now I'm doing a lot of force and I'm using a lot of energy, but I'm not accomplishing anything. I'm not actually doing any work. So one of the two terms that oftentimes gets confused with each other is heat and temperature. Now heat is strictly the energy used to cause temperature. It's what actually is causing a temperature increase. Or if you pull energy out, you're causing the decrease in the temperature. So heat is literally the energy moving from one object to the other. Temperature, on the other hand, is the actual measurement of average kinetic energy of the molecules. So now we're looking at the movement of stuff. So think of it like energy is what causes temperature. So heat is the energy, it is what is causing the temperature to occur, and temperature is just the actual measurement of something moving. There are two main ways that you can possess energy. One is the energy of motion. That's called kinetic energy, and you've probably learned about it before. Basically, it's an object of something that is moving. So you have a certain mass, that's what the m stands for, and you have v, which is the velocity as it's traveling, and you get the kinetic energy. If you increase the amount of kinetic energy, you're going to increase the amount of work that can be done, which kind of goes hand in hand, makes sense. If you think about it, you're doing more work, you're probably applying more energy. The big thing with kinetic energy is it has to be a movement that occurs. If there's zero movement, you have zero kinetic energy. Think about it. Put a zero in place of v, it comes out to be zero. The other type of energy that you can possess is called potential energy. And this is the stored energy. Think potential. You have the potential to do something. Think like a spring that's coiled up. Has lots of energy built up into it. Potential energy is just simply the mass of the object times the force of gravity times the height that it's at, or the distance, depending on what you're looking at. But potential energy is stored. Notice there's no movement here. So the neat thing about potential and kinetic energy is that potential energy gets converted into kinetic energy as an object begins to move. Think if you're sitting on top of a cliff. If you're up on a cliff, you have a potential energy up here, and then as you're falling, that energy is converting from potential into kinetic. Now, why would we be talking about all this stuff moving when we deal with chemicals? Well, water can be a good example for me to use for this, because water has both kinetic and potential energy. If you look at the actual water molecules, they're moving around. Even in a solid state, when we talk about them being at their lowest amount of energy, they're still vibrating slightly. So you still have that kinetic energy. But if you look at the bonds found within the water molecules between the oxygen and the hydrogen, now you've got a lot of stored energy. That's your potential energy. So all molecules have kinetic as they're actually moving around themselves, and then you also have the potential energy found inside the bonds themselves. So since we've had all these different formulas, we probably need some units to work with. Remember, we would like to have our units so we don't get lost. Because when you get lost, that's when the Shankopotamus comes and gets you. I hope you didn't forget about him because he didn't forget about you. But one of the most important units that comes with thermodynamics and thermochemistry is the joule, which is a capital J. So it's the SI unit, or the standard unit for energy. And you can kind of break a joule down into other parts, where a joule is literally equal to 1 kilogram times the meter squared per second squared of an object. Basically, it's kind of the measurement found within kinetic energy. If you think about mass times velocity, velocity is meters per second. And if you remember the formula, kinetic energy is 1/2 times the mass times meters squared. So you get your meters squared, second squared, and you get your mass, your kilograms. More often than not, we use kilojoules because it's a bigger unit to work with, and we're usually working with larger measurements. We get the name Joule from that guy, James Joule. Now, James Joule was a physicist who worked in a large variety of different places, dealing mainly with energy transfer. So we named the unit in honor of him. Another unit of measurement you may be familiar with is the calorie, and this is calorie with a little c, not the same thing as the capital C, which is found on food. This is used to measure energy within a chemical reaction. It's a non-SI unit, meaning it's not like a metric unit, but we use it a lot of times in chemistry and biology and biochemistry. And there's two kind of main ways you can define it. One is that a calorie is literally the amount of energy needed to raise 1 gram of water 1 degree Celsius. And then another way to define it is 1 little c-cal is equal to 4.184 joules. And that's an exact number. It's not like a rounded number. So 1 little c-cal is equal to 4.184 joules. It's also the amount of energy needed to raise the temperature of water 1 degree Celsius with 1 gram. Now there is one other type of calorie that you've heard of before, and that's the food calorie. That's the big C that you see on all of your little wrappers and stuff like that. And 1 big C calorie is equal to 1,000 little calories, or 1 kilocalorie. And the kilocalorie thing I put on there is because if you actually go to other countries where they use the metric system, which makes a whole lot more sense than what we use, they actually measure in kilocalories, which is kind of cool. Alright, so now you have a pretty decent base to begin with thermochemistry. We're obviously going to expand on this a whole lot more as we kind of move through the rest of this unit, and we're going to talk a lot more in depth about it. Make sure you remember these units. They're very important. Make sure you look back over those formulas too. Write down any questions you might have. Bring them with you to class. We'll talk about it. Catch you later.